When a violent supercell descending over isolated farmland strikes the ground, it leaves few traditional structures behind to measure. On June 20, 2025, a tornado struck rural Ransom County, North Dakota, near Enderlin. It carved a visible scar across the prairie for 12.1 miles. The National Weather Service initially rated the event as an EF5, with winds estimated at roughly 160 miles per hour. 4 months later, following forensic analysis, the rating was upgraded to an EF5, with winds exceeding 210 miles per hour. It was the first EF5 recorded in the United States since 2013. This upgrade was based on evidence from a train derailment. The tornado struck a freight line, derailing 33 cars with a force that exceeded standard meteorological expectations. Because the storm hit a moving train in an unpopulated area, the National Weather Service used the data to update its methodology for quantifying the most violent winds on Earth. Operational tornado research faces a persistent measurement gap. Traditional surface instruments, such as anemometers, rarely survive a direct impact from a violent funnel. This is a departure from other extreme weather systems. During a hurricane, dense networks of hardened weather stations can broadcast live wind speed data throughout the duration of the storm. Since direct measurement at the surface is nearly impossible, meteorologists must work as forensic investigators, analyzing physical destruction to infer the velocity of the winds. This process creates a reliance on human engineering. The final rating depends entirely on the specific man-made structures the tornado happens to strike. If a tornado tracks strictly through open fields, its true intensity remains invisible to the standard scientific record. In 1971, Dr. Tetsuya Teodor Fujita introduced the original Fujita scale to categorize tornadoes based on the damage they caused. The original scale was based on visual assessments and assumed that an F5 rating required winds between 261 and 318 miles per hour. In 2007, the National Weather Service adopted the enhanced Fujita scale. This system replaced visual estimation with structural engineering formulas. Engineering studies show that typical wood frame houses fail at lower wind speeds than previously assumed. A well-built home can be completely swept from its foundation by a 166-mile-per-hour gust. This lowered the official threshold for an EF5 rating to winds exceeding 200 miles per hour. The transition to the EF scale standardized tornado ratings as a rigid, math-based engineering process. The core of the scale is a matrix of 28 specific damage indicators, each with defined degrees of damage. These indicators cover a variety of structures, from hardwood trees and farm outbuildings to high-rise hospitals. Engineers calculate wind loads by examining microfailures on these objects, such as the sheared anchor bolts on a toppled communications tower. This system has a critical limitation. If a tornado does not strike one of these 28 building types, surveyors cannot officially rate the storm at its peak velocity. This requirement leads to a rural bias. Because violent tornadoes often strike open land, the official record showed a 12-year gap in EF5 ratings. The Enderlin tornado tracked through open fields and hit a moving train. Neither of these existed on the official list of 28 indicators. Without a standard building to destroy, the National Weather Service was initially unable to verify that the Enderlin storm had reached EF5 intensity. Surveyors resolved the discrepancy by applying forensic kinematics to the trajectories of massive, non-traditional objects. Experts utilized a 2024 study on the debris trajectories of large, compact objects to calculate wind speeds without relying on the standard building list. The Enderlin tornado tipped multiple loaded grain hoppers, each weighing 286,000 pounds. This 3D model illustrates the mass involved. The most significant evidence was an empty tanker car weighing 72,000 pounds. The storm lofted this car through the air, depositing it 145 meters from the tracks. Forensic calculations on this displacement show that lofting an object of this mass beyond 50 meters requires sustained wind speeds well over the EF5 threshold. By analyzing the movement of heavy industrial equipment, researchers successfully bypassed the architectural matrix to prove the storm's power. Physical damage modeling is now being used to verify data from modern active measurement tools. Doppler-on-wheels units deploy directly into storm paths to capture high-resolution velocity scans from inside the funnel. These units recorded a historic event during the 2024 tornado in Greenfield, Iowa. Mobile radar clocked instantaneous wind gusts between 309 and 318 miles per hour inside the Greenfield funnel. This velocity was measured 44 meters above ground level, rather than at the surface where buildings are situated. Because the measurement was transient and elevated, and the town lacked high-end structural indicators to verify that force at ground level, Greenfield was not rated as an EF5. Active radar data shows that 300-mile-per-hour kinematic environments exist, though the official record requires physical evidence from the ground. There is an ongoing tension in severe meteorology between mobile radar observations and the engineering requirements of the ground-based scale. The 2025 Enderlin upgrade resolves this discrepancy, applying the rigid rules of the enhanced Fujita system to industrial evidence. The EF scale is evolving to incorporate forensic trajectory data from non-traditional indicators. Scientific evidence is not limited to destroyed buildings. In Enderlin, it took the form of warped steel tracks in an empty field. Quantifying the absolute limits of nature's fury involves decoding the physical trajectories of everything the wind leaves behind.